Hello, everyone. This is Calculus Fall 2020. My name is Scott Grizzard from the University of South Florida. I didn't just forget my name. It's one of those mornings. And we're talking here about Quiz 9B, which is on the inverse trig stuff. So let's go ahead and look at it. Okay. So, and I've got notes to myself in the corner, so I'll forget anyway, but at least I tried. Okay, so Daffy's wrong here. And watch out, because this is a common mistake to make, especially if you know it's wrong, but then you're in a hurry on the test, and you're like, oh, what was it? Just a negative arc? No. And it's always really easy to mess this up if you see the -1 up there, right? Because remember that arc cosine is that cosine -1, which is a totally different thing than 1 over cosine. 1 over cosine is called secant. Okay. So Daffy is wrong. That's what it is. Okay. So my little introduction, I'm going to say, well, I want to show dy over dx equals -1 over the square root of 1 minus x squared. My strategy is going to be let y equal arc cosine of x. So take cosine star of both sides. Take the derivative in terms of x. Dx of both sides. And then use the triangle trick. To rewrite the right in terms of x. That's a little long. I could just stop this, would use the triangle trick to get rid of the x. And the strategies vary. I kind of want to rewrite what I want to say. Even though I just wrote it there. I mean, I kind of can get away with it, but I kind of want to, I want people to know what I'm trying to say. Because that, helps. So yeah, Daffy's wrong. Here's a hint. Daffy's almost always wrong. Bugs Bunny is usually right, but Daffy's usually wrong. That's not always true, but these are Daffy used to make an appearance on all the tests, and then people got annoyed by it. And by people, I mean other instructors. The students thought it was funny. Daffy got dropped. They also figured out that Daffy was always wrong and Bugs was always right. And apparently students were figuring out that Daffy was always wrong and Bugs was always right. So, which I thought was appropriate, but, so 1 to 5 about the strategy, about the intro. So we got 1, 2, yeah. People used to say that I had too much personality to be a mathematician or an economist. So, I thought it was fun. So the strategy is just a brief overview of what we're going to do, kind of hitting the highlights. And remember, even if I just had this, right, on a test, I would get a lot of points, right? If that's all I had time to write, I would get a lot of points. So just in English, what I'm about to do. So the body. So I'm going to say let y equal arc cosine of x. Then cosine star of y equals cosine star of arc cosine of x. Now, which equals x, since cosine star is the inverse of arc cosine. Now, I always get this question, can I just write do I have to write the cosine star? No, but you can't really say that cosine is the inverse of arc sine. You can say that, on the domain of arc cosine, right? You can say that in the range of arc cosine, cosine of arc cosine is the same, but you can't say this word inverse. But you can say like the range of or whatever. And it's kind of an abusive language, technical fine point. Right. And would you have to say that? Could you just take cosine star on both sides and skip this step? Yes, if you have an introduction and, it's one of those things that, no, you don't have to have it, but you better have a bunch of other stuff that you don't really have to have, if that makes sense, right? I need to have like some, the level of detail doesn't have to be, I don't have to have copious amounts of detail, but I have to have some. And this is one of the details under the sum. Right, I have to have, this or this little detail or this little detail. I need enough little details. So this is one of those little details that count towards enough. There we go. Okay. And then, so now what I'm going to do is I'm going to take the derivative of both sides, d over dx of cosine of y equals d over dx of x. So I do a little chain rule action here, and I get d over dy cosine star of y times d over dx of y equals 1. I might write chain here. I don't have to. Again, that's one of those little details. You need to have enough details. You don't have to have all of them. And then that means that sine, negative sine, that detail is important. The fact that the derivative of cosine is negative sine and not sine, that's very important. Times dy over dx equals 1. Which means that dy over dx equals negative 1 over sine of y. And then, because I'm multiplying this over, I need to say where y, again, this is one of those details. Y in 0 pi. In other words, I've lost the endpoints. Which is, you just need to kind of mention that. Or you don't have to. It's one of those details. Okay, so now I've got sine y here. I'm going to do the triangle trick. I like to do my triangle tricks off to the side. You can do them, in line. That's fine. So I've got sine of y. I know a couple things. I know that the cosine of y equals x. Okay. So I'm going to put 1 as my hypotenuse. I'm going to have cosine be the adjacent. That's x. And this becomes sine of y. And here's cosine of y equals x. Right? Because I made that 1. Then I've got SOHCAHTOA here. So cosine equals x equals adjacent over the hypotenuse, and then sine of y equals the opposite over the hypotenuse. So I basically need to solve for the opposite. So the opposite squared plus x squared equals 1 squared. And I just kind of do this over to the side as notes. Now, is that clean? Is that perfect? If I was in a Bridge to Abstract Math class, I would probably get, no, you need to make this perfectly. And then how do I determine where things go? Well, I start at the top here. So what I have here is this. Cosine of y equals x. And I might even write, we can even write that over the side. I have cosine of y equals x, and I want sine of y. Now, wouldn't it be nice, right? This is adjacent over hypotenuse, and this is opposite over hypotenuse. Now, wouldn't it be nice, little Beach Boys there. Wouldn't it be nice if the hypotenuse was 1? Wouldn't it be nice if the hypotenuse that we have to divide by really was 1? That kind of thing. Wouldn't it be nice? So, wouldn't it be nice if the thing I had to divide by was 1? Yeah. I'll make it 1. How do you feel about that? That's a good question. So, how do we feel about 1 to 5 making the hypotenuse nice? Now I have that song stuck in my head. Wouldn't it be nice? Right? Just, wouldn't it be nice? Well, I can do that. I get to, but once I label that 1, this becomes x. Right? That's my adjacent. And now I'm looking for the opposite side. Well, that means the opposite. So I'll just I'm going to move the triangle trick stuff up to give us a little bit more room here. Oop, I don't want the lost endpoint bit. That's actually part of the proof. Let's move this work up here. And then let's move this bit right here. Right here. Now, this is not a nice, this triangle trick business is not exactly a paragraph, nice little proof bit. So as I said, if I was in a major, if someone was reading this proof that, I want to do, I wanted to impress or something, right? This is not the thing that mom's going to stick on mom's going to stick, not going to stick this little bit on the refrigerator, right? But what I want to do is now I want to solve for this. So I get that opposite squared equals 1 squared, 1 squared, right? The hypotenuse equals x squared plus the opposite. Or I could say sine y squared. Okay, and now what I want to do is I want to solve for sine. So what I do is, okay, so that means that I move this over to this side and I get sine squared y equals 1. Let's see, that went there. That took a negative when it did that. So this basically just came over there. So that becomes 1 minus x squared. So that means that sine y, I'm getting lazy and I'm leaving off my parentheses. Sine y equals the square root of 1 minus x squared. So I just come over here and I go -1 over the square root of 1 minus x squared by the triangle trick. Okay, thus, and then I'm done, but I give me a little tagline. D over dx of arc cosine of x equals -1 over the square root of 1 minus x squared. Q, E, D. Okay. So how do we feel about the triangle trick overall there? So let's see. Stop. Start. All right. Why wasn't I a music major? Because I don't love it as much as I do math and econ. I mean, honest answer. Okay. All right. And then overall for the whole proof, so let's see, the whole proof, 1 to 5. So again, this idea was that I took the model for sine and I just kind of made me a new proof for cosine. Now, if you look it up online, you're going to get, there's a couple little variations on this theme. Okay? So if this makes you unhappy, if the triangle trip makes you unhappy, if the triangle trip makes you unhappy, you can do this. There's an alternate to the triangle trick. And the alternate is to do this. Okay. Well, I know that sine y, this is the alternate. I do sine squared y plus cosine squared y equals 1. And this was x, so that means that sine squared y plus x squared equals 1. And that means that sine squared y equals 1 minus x squared. And that means that sine y equals the square root of 1 minus x squared. So if the triangle trick is seriously keeping you up at night, you can get away without using it. You can use the Pythagorean identity. Now, you're actually doing that already when you do the triangle trick. The triangle trick is a little bit more flexible, though, in that I don't need to memorize all of those identities. And that's especially true with the tangent one. Okay? So the Pythagorean identity with tangent is actually something I have to look up. I don't really have to, because I can figure it out from the other one. Right? But that's something that I don't keep in mind. Sine squared plus cosine squared. I got that. It's a triangle. Right? But the other ones, I either have to look it up or I have to derive it for myself. And I can, right? I mean, I can sit up here and I go sine squared y plus cosine squared y equals 1. I divide through by sine squared and I get, okay, sine squared. So basically what I do is I divide through by sine squared. Right? And that gives me one of them. Right, so I divide everything by sine squared, and I wind up with 1 plus cosine squared over sine squared is cotangent squared equals 1 over sine squared, which is cosecant squared. Right, I could sit there. I could sit there. This is an x. That's a y. So I can remember how to do them, right? And then the other one, I sit there and I do the other. Plus cosine squared y equals 1. And now I'm going to divide by cosine, and I get cosine squared. There's my tangent squared. There's my 1. And there's my 1 over cosine squared, which is secant. Right? So, I mean, I can do it, but these are like 3 things I have to memorize. Whereas the triangle trick, once you've done it a few times, it can get intuitive. But you can get away without figuring that out. So you wind up with tan squared y plus 1 equals secant squared y. Now, for me, this is harder, but because it's something I have to memorize. Whereas, the triangle trick is something I understand. But you can do this. If you're absolutely horrified by the idea of the triangle trick and it's something that brings you dread, and this is something that brings you joy, go for it. And it does make for something that looks neater on the page, right? By the Pythagorean identity, right? That's one of those things that, if I was in a geometry, if I was in a proof class and I say, by the Pythagorean identity, this is true, and then I go forth, it's going to look better. As far as the person who's doing it. One other detail that I didn't mention, that I should have, was right here. Again, one of the details that makes up enough, right? So I don't have to mention every single one of these details, but one of the details that I could mention to get enough detail is y is in 0 pi, so sine of y is greater than 0, and I don't need the plus minus. So that's one of those things that, it makes up the sufficient detail, if that makes sense, right? I just need enough. Okay, so 1 to 5, how do we feel about it now? Let's see. So stop. Oh, no, I can't end the poll yet. I figured out that, I told you this before. I figured out that if I'm on the poll thing and then I stop the poll, it will let me keep my options. Alternative to triangle using the identities. Start. So, it's whatever makes you happy. As I said, you can get away with using the identities if that's the thing that makes you happy. The theme for doing the proofs for cosecant, cotan, once you know two of them, once you understand the proof for tangent and sine, the others are variation on a theme. So I have never, ever, 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 ever once memorized the proof for the derivative for arc cosecant. All right. If somebody put that on a test, I would have to take 5 minutes to rederive it. No idea what it is. I don't even know what it is now. I am teaching calculus, teaching this section on the derivatives of these trig functions, and I have no idea what those are. All right. Cotan is -1 over 1 plus x squared, I think. I'll have to do it to check. But the ones that I know off the top of my head are sine and tangent. I remember that cosine's the negative of the sine one. And that's all I memorize. Right? The other stuff, if you asked me that stuff, I'd have to sit here and do the proof. It's the only way I know it. And so I don't want to give you this impression. It's like the double angle formulas, right? I don't know the double angle formula off the top of my head. I know what the picture looks like, right, that I need. So, I can figure it out based on the picture, but I don't memorize those things. I don't teach Calc 2. I don't need that every day. And I don't teach pre-calc. They won't let me teach pre-calc anymore. So, I did a bad job when I taught pre-calc. And the bad news is they won't let me teach pre-calc anymore. The good news is they won't let me teach pre-calc anymore. So, all right. Okay, well, let's move on then. So this right here, this limit of arctan of e to the x. All right, so I'm going to go off to infinity. I'm just going to do the exact same thing I did before. And I showed you there's an example 4 in the book in section 3.5 that does a few of these. But I'm going to say that's sort of like equals arctan of e to the infinity. And as I go off to infinity, arctan, that just goes to infinity. By the way, I cannot do this trick with tangent. I can do it on tan star. So if I had something like the limit as x goes to 0 from the right of tan of let's do e to the negative infinity. Let's do e to the infinity tan of e to the x. I actually can't do this because tan is not continuous. So I can't just sub in the infinity here. There's a subtle thing. I can on tan star because tan star is continuous over its domain. But tangent isn't. So you can't just sub in. You kind of have to feel for it. I don't mean that to distract you. I'm just like, keep in back of your hand that this trick works because these functions are continuous over their domains. Okay? Now, I can restrict the domain and then do it, but I have to be careful. This would be the limit as x goes to negative infinity, by the way. So tan is not continuous over it. I can't do it here. Technically, I can't, not continuous. Whereas tan star is continuous. On its domain, okay? So the fact that 0 here, I'd wind up with 0 right here, that would be fair. I can kind of do it here, 0 right. So when I'm figuring it out, I'd stick 0 here, I'd stick negative infinity here, I'd get 0 right, and then I'd see that this was tangent, and I go, okay, I can't actually do the continuity thing, but I know it's going to be 0. So what I'm going to do is I'm going to make it tan star because that's in the domain of tan star, and now I've got a continuous function. Or I'd write some technical thing that says, oh, I can do this. So that's just, I don't mean to like confuse you. I just mean to keep you in mind. This trick works because arctan is continuous over its domain. So I'm going to write that here. I don't let that confuse you if it is. But it is something to just, let it itch the back of your mind a little bit. That there are, when I do this like trick, there's like rules to it. I know it doesn't seem like there are rules, but there are actually rules. So now I'm going to do arctan and infinity. Well, what happens? What angle would give me an infinite? So when I use the star, the domain of tangent and sine are restricted to those things. The domain of cosine. I'm sorry. Did you say? I'm sorry. I didn't. Is it always restricted? No. So on cosine, it's restricted from to 0 to pi. I'm sorry. I'm getting it backwards. Whereas on sine, it's where sine and tangent are negative pi over 2 to pi over 2. Sine with the endpoints, cosine, tangent without the endpoints. Which brings us to this question. If I want on this right circle here, if I want on this right piece of circle, if I want the length of this tangent line to go off to positive infinity, which side am I headed to? Am I headed to this side or am I headed to this side? Right, so this half circle, I don't know why that just happened. This half circle represents, the happy place for tangent. Now, if I want the tangent line to go off to negative infinity, what do I have to do? Right, remember that tangent is the length of this, is the length of the line from here to the base, technically. And the fact that it corresponds to what we think of as the tangent line is is why that word is. Why do we use the word tangent to describe these things? Well, this is why, right? It comes from the circle. So as I go off to positive infinity, right? As I go off to positive infinity, arctan, the thing that makes tan go off to positive infinity is positive pi over 2. And I can think of it like this. That's because tan to infinity as y to pi over 2 from the right. And I could say right, but then it's just a number. So how do we feel about that? 1 to 5. Is Scott broken? I assume you mean because I wasn't a music major? Okay. And this problem is hard. I mean, this problem is something that I might ask on a bootleg. I wouldn't want to ask this on a test. This problem is really hard. So this idea of arctan, what's going on, you kind of have to think of it in terms of the other thing. And this is a hard problem. Right? This is a really hard problem. If it's not for you, that's awesome. I'm on board with this. I could say it goes off to infinity. Let me write that. Yeah, I'll just write this. Pi over 2. Pi over 2 plus is also a good answer. Pi over 2 plus, once you say what it is, it's pi over 2. But, you know. Okay. That's a hard one. Someone in Twitch, she was like, oh no, I could be, you know, I didn't mean to be bragging. It was hard for me. I love it. I didn't mean that. Okay. This one is our old friend x to the times e to the negative x. You will see this function again and again and again and again and again and again and again, because this function is the basis for so many things in statistics, in medicine, chemistry. I keep mentioning it because it just keeps coming up. So it's one of those functions that, at least for me, I'm like, let's ask this a ton of times. Because it's actually one of the real ones. So, okay. So I'm going to do the product rule method. You can put this on the bottom and do a quotient rule, but what the heck. So the journey of x here, if I wanted to do the journey of x, right, it's x goes, and this is just going to go in. This is x. This gets negatived. Negative x. And then I've got kind of a e to the negative x here. And then this little x thing gets just shoved onto it. So then I've got x times e to the negative x. The last thing that happens is a product rule. There's going to be a chain on that side. Okay, so that's the journey of x, if that helps you. At this point, I probably am wasting time doing that, but that doesn't mean it's not a good idea. By the way, on the test, I was immensely pleased that you guys did this. I was reading it. You guys didn't, for the most part, you know, some people who didn't do this did mess them up. But you guys, by doing, when you wrote this, it was beautiful. Everyone could figure out exactly what you were doing. It was just, you know, the graders were all like, oh my goodness, let's grade Scott's first because, you know, his students write things well. Have Heaven forbid. So everyone could figure out what you were doing. It was good communication. And even when you made mistakes, you got more credit than other people did because everyone could figure out what you were doing. And it was all communicated, so you got all the communication points. It was lovely. I was so proud. And then I'm going to have a chain here. So my U here is going to be, here's my U. My U is going to be negative X. So I'm going to have 1 times e to the negative x, that's baggage, plus x, times the derivative here. So this is going to be the chain d over du, e to the u, times d over dx of u. This is going to be e to the negative x plus x, e to the u, times the derivative with respect to x of negative x. And then I'm just going to put in my baggage. Sub my stuff back in, e to the negative x times negative 1. And then I'm just going to leave it like that because no one's saying factor. And this looks like a lambda. X, e to the negative x. Okay, that fixed it. My x was looking a bit like a lambda. Now it looks like... Now it looks worse. I keep making it worse, don't I? X, e to the negative x times negative 1. There we go. So 1 to 5, how do we feel about that old little throwback problem? Grades, so people are asking about the grades on test 2. I have no idea. Okay, last time she sent out an email at the very last minute saying, don't release your grades. And then I did, and I got into trouble. And I don't know what's going on. I looked at the grading. It's not completely finished for my test yet. If the graders don't have it done by tomorrow morning, I'm going to stick my graders on it. If the graduate students don't, and I still kind of want to go through them because I don't really trust the graduate students. I trust my graders more than I trust the graduate students because my graders care. I think it's because I got to choose my graders for 1. And 2, they actually care because they're kind of like, they're graders. They actually care. They're not cynical yet. And 3, you can actually fire these people. So when they get bad, you can sack them. We only have the good. It's not that it's not like they're operating under the threat of being sacked. It's like we got rid of the ones that weren't very good. So the ones that are left are good. You're kind of stuck with graduate students because they're not really, their primary job is not to be an employee, it's to be a graduate student. All right, so this last one, which is more information than you wanted to know. I'm going to write over to the side here that the d over dx of arctan of x equals 1 over x squared plus 1, or 1 plus x squared. I'm just going to write that over to the side. Okay. So, I don't know what's going on with the internet. So all day yesterday, people that were trying to watch me on Twitch, it was like weird. And then, it's not, I did an up down on mine and, it was fine. So I don't know what's going on. I think it's the down speeds. Okay, so now I've got a chain rule here. Now, it's just a thing. When I do these non-standard things, I kind of just write them off to the side. And later when we do, and this is a good habit to get into, because when we do integrals or antiderivatives, we're going to want this kind of little table going on. And I'll talk about that later, of kind of making a table of the original function and the derivative. But this is, I kind of on the right, I kind of just say, okay, well, this is the original function here, the derivative here. So I've got this u thing going. I mean, it's a chain rule. So I'm going to have d over d u. So this is a chain. I'm going to have d over du of arctan of u times d over dx of u. And I am kind of skipping a step there, so I hope you don't mind. And then I'm going to take this, so this is going to be 1 over u squared plus 1 times now the derivative d over dx of u equals 1 over u squared plus 1 times, well, I should actually write what this is. So this is d over dx of x cubed. So this is 1 over u squared times, so 1 over u squared plus 1 times 3x squared. Now, when I sub in my baggage on these, and this is one of these annoying things, is that when I sub in my baggage, especially if this was x squared, which is one of those things that people like to ask, which is horrible because it encourages mistakes, and that's why they like to ask it. Let's write it, getcha. I'll talk about that in a minute. That is a good question. So one of the getches here is that this u is x cubed, and I've got a u squared here, so I need to be careful when I do that. This is 1 over x cubed squared. And if this was x squared instead of x cubed, a lot of people would just write 1 over x squared plus 1. Right? Because you missubstituted because there was already a square there. So watch out for that. This is one of those places where you can get a gotcha. So watch out for that. That's all I'm saying. Times 3x squared. And if I wanted to simplify, again, if I want to, not necessary, it would be 3x squared over x to the 6th plus 1. Okay, so 1 to 5, and then there was a question about doing it the other way. Oh, crud. So this is part C. 1, 2, 3, 4, 5. Okay, so there's this other thing that I sent. So there's this other way to do it, which has been alluded to in chat. And I'm okay with you doing this, but I keep in mind that you can do it the other way, because otherwise, if you had something like arcsine of arcsine, you'd wind up in trouble. But you can do it like this. Let y equal arctan of, what was it? X cubed? Yeah. All right, then that means that tan of y, it's really tan star of y equals x cubed. And now I take the derivative of both sides, and I end up with d over dx of tan y. I'm just going to do it. So if you, I'm skipping steps, so I'm just going to note skipping steps. All right, and then if I mess it up, yell at me for skipping steps, because then I'll mess it up. So I'm going to do here, the derivative of this is 1 over cosine squared of y times dy over dx equals, and then I take the derivative of this, and I get 3x squared. All right, so I can do this. Note, I'm skipping steps. And then what I do is I kind of just solve for this. So I have dy over dx equals 3x squared cosine squared y. All right, and so what I have is tangent. So then I do my little triangle trick here with tangent. I have the tangent of y equals x cubed. And what I want is, and this is one of the reasons why this is so much more flexible, this triangle trick is much more flexible than the other ones. So I've got the tangent of y equals x cubed. And And then I've got and I want cosine squared of y, or just cosine of y, but cosine squared of y. All right, so what I'm going to do is I'm going to make the adjacent, this is opposite over adjacent, I'm going to make this x cubed. And I want cosine squared, so I need to solve for the hypotenuse. And so the hypotenuse, hyp squared, is going to equal 1 squared plus x cubed squared. Which means that the hypotenuse equals 1 plus x cubed with a square root on top of it. So I wind that up. So I have cosine. So cosine of y equals the adjacent over the hypotenuse, 1 over square root of 1 plus x cubed. So cosine squared of y equals 1 over 1 plus x cubed. So I wind up with this equaling 3x squared times 1 over... I messed it up because I have an x cubed there and an x to the 6th there. What did I do wrong? And this is one of the problems, is you mess them up. And that, and what I want is cosine, so that's 1 over that. The tangent was this. Somewhere I have messed this up. Can someone figure out where it was? It wasn't here. The square, oh! It's right here. There it is. So this right here should be 1 plus x to the 6th. There we go. I found it. Never mind. Okay, so now I wind up with this times 1 plus x to the 6th. Okay? So I can do it that way. Whether or not you want to do it that way is up to you. And again, I forgot to square my 3. I forgot to multiply my 3 times 2, right? I forgot the 1 plus x to the 6th. So, you know, it's you can do it that way. You can do it that way if you choose. Okay. If that brings you joy, if that's math joy for you, go for it. That is a perfectly legitimate way to do it. Okay. This one here is the product. And it's going to be d over dx of x squared times arcsine of x plus x squared times d over dx of arcsine of x. And that is going to equal 2x arc cosine of x plus x squared times 1 over the square root of 1 minus x squared. Okay. And then I'm done with that one. So how do I feel about that 1 to 5? So let's see. Part D, stop, start. I have spoken for 50 minutes. Oops, sorry. I miscopied. I miscopied my baggage. Thanks. I just miscopied my baggage. I wasn't trying to take a derivative or anything. I just, my brain arc and then cosine and arcsine. Arcsine is a weird word, isn't it? You don't really see a C and an S like that together. Usually it's a K and an S, right? Like a bricks. Arcsine. Okay. All right, any questions for me? Yes, you can. So when you take the derivative, you can just write 1 minus x. Yes. So you don't need to show all the steps. You don't need to rederive this every time, right? You only need to rederive it if it says derive, like here it said prove it, right? So you only need to prove it if it says prove it, right? But here I don't need to do that, right? I could, right? I could sit over here and do that, but it'd take me another 20 minutes, and I don't think I should. Maybe for the 5 p.m. I'll do that, so that they'll do the alternative. But I could do that if I so desired, but why? Does that answer your question? And the fact that you want to is actually something I really like, because the fact that you say, well, why don't I just make it y and then do the both sides? That means you thoroughly understand the process. The fact that you want to do that is good. The fact that you look at that and say, well, I want to move this over to the other side, that's good. That's a thorough understanding. That is a much higher level of understanding than memorizing what the thing is, right? That's good. You just don't need to do it every time. So the fact that you want to do that is a good thing. But you don't need to. Any other questions? Okay. So that's it for the quiz review.